ideal distance? That's all I focus on. That's all I did at least in that. That's okay. I kept noticing this writing. It was right in that place. I don't remember. And I think Krishna is on that place.
Send me that link. No,
that's not connected to it.
लिख दो ऑडियो ये ना हवा ये तो कहाँ चल रहे हैं फिल्टर नहीं आ रही गंदी हो गया बहुत नो फिल्टर सारी लेगा मैं बेंच तो बटन दबा के इधर ही ना कर दूँ ऐसी वही तो कैसे चेंज कैसे बोल रही है ठीक है शेम है कोई नहीं बैठा रहता कुछ तो आएगा हाँ हाँ फिर ले लाते हैं वो घंटे को दिल्ली के सैनिक कॉम में खिड़की बन गया थोड़े हो प्राइस अभी बाबा कंपटीशन हो रहा है जो भी पाकिस्तान में पूरी बारिश नहीं इंडिया में कॉम्पिटिशन हो रहा है एक बंदा पहले गया 15 sitting in office.
Let's pause the message group. The sir is not going to ask for that.
समझ गया हाँ मम्मी से कुछ कही ना क्या होगा उसको नौकरी पे
तो काम नहीं कर रहा तो छोटे मोटे लोगों को काम करना पड़ता है
भाई बड़ी बात करता है
छोड़ देते जो काम
अबे कर देता मैं वो सीसी के थ्रू पा गए
30% लेके आता है
31% था वाह भाई 30% सीसी में पास करते हैं सीसी के थ्रू आ गए थे नहीं तो मैं वो भी गलती से क्या हुआ मैंने ज्वाइन छोड़ा
वालों की है
और तू मेरी
इंदौर हो गया इंदौर हो गया
इंदौर तो कौन
इंदौर तो हो गया
क्या कर रहा है भाई रचित?
अरे अरे
रचित इलेक्ट्रिकल इंजीनियरिंग मत कर
ये सीख लिया भाई मैं
चला
कहने
दे,
नहीं
शायद चला दे, रुक जाओ करने दो।
चलने देना तुम्हारा
क्या दिख रही है यार
क्या प्रॉब्लम है
अरे
देना जल्दी पे दे। ये पूरा खत्म कर दे। It's not working.
It is from the security. Let's just quickly go through what I was trying to do last time. It's an undirected graph is said to be connected if there is a path between any two pair of vertices. And you can check the graph whether it is connected or not. You can just apply the BFS starting with a new vertex. What happened to this? Yeah, so then we have what is known as articulation points or a cut vertex. It's a vertex whose removal actually disconnects the graph into two parts. And so we were looking at the problem of finding in all the articulation points in the graph. So one brute force algorithm is just to remove that vertex and all the adjacent, all the edges which are incident on it, and then run BFS or DFS on one of the remaining vertices. If the graph is still connected, then it's not a articulation points. Otherwise, it's an articulation point. Then we have seen that so this is an order V into E algorithm. So we wanted a faster algorithm for this. So let me just do what I did last time, and so they probably give an equivalent algorithm for it. So I started with A. Okay, then let's say that I go to C. Then let me go to E. From E I have a packaged A. From C I could go to B. From B I could go to D. from D I could go to G, okay, and from I went to F, and you have a back edge from D to F. So last time, so essentially I looked at the DFS of the tree, then I did define the levels of each of these vertices. Then I defined something. So you can also do, for that you have to traverse the graph again. Instead of doing that, we can also work with the discovery times. Discovery time also, so what essentially I wanted is that from this vertex, from this subtree, how far can I go back, right? So that's exactly what I wanted to keep track. So that can be kept track by using the discovery times. The discovery time of this is 1, this is 2, this is 3. So then you're going backward. So the finish time of this will be 4. So I'll write it as 3 by 4. Then this will be 5, 6, 7, 8, 9, 10, 11, 12, 13 and 14. Right. So I don't need the finish times probably. What I need is and you can also define the pi function, which will actually help you to. Pi of v is u. In other words, when I look at the edge u comma v, so if v was discovered through u, the pi of v will be u. In other words, the pi function will give you the DFS tree of the this thing. So now I can define L of v. So L of v is essentially the lowest level that I can go back from this particular vertex. Okay, so how do you define? So this is going to be the minimum of, minimum of discovery time of v. That's one item. Then you look at every outgoing edge from this particular vertex. So if you have u comma v, this is an edge. Okay. So if this is an edge, it can be two things, right? Either it can be a back edge, or it is a tree edge, right? If it's a tree edge, then what did I say? If it's a tree edge, then the question is from here how far can you go back, right? So it is an edge, and I'll write it as a tree edge. Okay. If this is a tree edge, then I want to look at L of u, right? So L of u will tell me how far you can go from here to the to a level which is above this, right? So which is essentially called as the ancestor. If u comma v is an edge, which is a back edge, okay. So if it is a back edge of this kind, then what is that should matter? The discovery time of. So discovery time of u, right? See if v. Yeah, so I think I should write it as v comma u. This is an undirected graph. So this is a tree. This essentially means that it's a back edge. If it's a back edge, then I want to know what is the discovery time of that particular vertex, right? So that's what it is. And if it's a tree edge, then I look at the LV of value of this. And so if that goes back here, then whatever is the minimum value of that. And I also look at the D of V. So in other words, L of V that I define will be smaller than or equal to D of V, right? So how far in the tree from this location, if I go down, so using a back edge, how far can I go back, right? That's exactly what L of V is actually looking at, right? So this is the lowest discovery time vertex V that I can reach by following the path downwards, right? By definition, for the leaf node F, what is the L value now? It's either minimum of 8, which is the discovery time of V, and there is only one edge which is going backward, right? So which is going to the vertex 5. So this has a this is the minimum of 5 and 8, which is 5. Now, so this again computed bottom up. So now this one, so it will look at the discovery time of it, which is 7, and there is a forward edge. So the L value of this is 5. So this will get a value of 5. That means from here, if you go down, you can go back to a vertex whose discovery time is 5, but not smaller than that. Okay. Now if I come here, again it's the minimum of 5 and 5. So when I come here, it's minimum of 5 and 5. So now I have to look at this side. This will be minimum of 3 and 1. So this is 1. So when I come here, this forward edge is 5, but this edge is 1. So this will be 1. When I come back here, this will be 1. Okay. So now, which are the points which are articulation points? So when do you say that a root node will be articulation point?
Can you explain the tree edge?
Sorry, I can explain.
The tree edge. I mean, just for the tree edge.
A tree edge is this edge, right? Pi of v is equal to u.
Yeah.
So that is a tree edge. So in other words, this is a tree edge. Okay, so when I look at the edge which is outgoing from here, so for this one I look at what is the L value of this. Okay, there may be more than one. So the parent is unique, but the children are not unique, right? So, so typically what happens is that you look at a vertex here, you look at the discovery L of v value, then you look at all the children of this in the DFS tree. Just look at the L value of all of them. Okay. Then also look at the all the backward edges from this vertex. Okay. Look at the discovery time of all of them. So you have the L values of all the children, you have the discovery time of this, and you also have the discovery time of all the vertices where this edge is at back edge. Among all these values, you are picking the one which is minimum. Okay. So if that is the value here, so when is this going to be a articulation point? So if you delete this, what happens is that there is a unique parent here. This part of the tree is cut from this, right? From every subtree here, there should be a value which is going back to this. Okay? In that case, the tree is still going to be connected. That means whatever children that you have cut, it should be connected to one of the parent of here, right? So for every child of this, if the L value, if so you are looking. Okay, so so if you are staring at the vertex V, take time to identify. So if you are at a vertex V, then you look at all the children of it in the DFS tree. So I want from every vertex to from every child of this, there should be an edge which is going back to this. In other words, my L value of u should be certainly smaller than or equal to, strictly smaller than. So even if it connects to here, right? When I delete this, then so this will be disconnected. So the lowest that it can go should be strictly smaller than discovery time of v, right? So for every edge v, if v comma u is a tree edge, that means if phi of u happens to be v, then the L value L of u should be strictly smaller than d of v for every u which is a child of this, right? If that is the case, then this is not an articulation point. But if there is one edge such that so the L of v value is greater than or equal to the discovery time of v is smaller than or equal to the L of u value, okay, then this is an articulation point, right? So that's what we say. So when do you say that a root node is going to be an articulation point? So this is true for every internal node. Okay, and so when do you this is the correct answer for every internal node except for the root node. Okay, when is that a leaf node is going to be an articulation point? So leaf node in the tree will not be an articulation point, because if you just delete it, you're not disconnecting anything from here. The leaf nodes are not the candidates. When is the root node is going to be an articulation point? Because nothing actually goes above this, right? This condition will not be true in that case. When is that the root node is going to be an articulation point? Yeah?
Yes, sir.
If it has more than one subtree, right? So if it has two children, right? So this is just a backend, this is not actually the child. Okay? If the root node has more than one child, then when you remove this, this is disconnected, right? In that case, this part of the tree will not be connected to this part of the tree, right? So, you compute the DFS of the tree, then you declare that all the leaf nodes are not articulation points, and look at the root node. If it has more than one child, then it's an articulation point. Otherwise, it's not an articulation point. Then from the bottom up approach, you compute the LV of value of all of them. When you go back, when you do this computation, just ensure that LV of the LU of the child is smaller than or equal to discovery time of this. That means from every child you have something which is going back to a level which is above this. If this condition is true, then you know that if this condition is true for every child, then you know that it's not an articulation point. But the moment you find one vertex where this condition is not true, declare that that's an articulation point and just keep going, right? In other words, you start here, keep going here, you come here. So now you know that this is an articulation point. Now you come here, this is not an articulation point, but you know that this is an articulation point because so from here nothing is going back, right? So this condition LV of value is smaller than or equal to this is not true for this, right? So because from here nothing is going back, right? So when you computed, when you came here, you knew that C and B are both articulation points because there is nothing which is going above this. And when you come here for this particular edge, there is nothing which is going back to this, right? So this is not an articulation point, this is an articulation point, and this is also an articulation point. Okay, so what is the complexity of this algorithm? In order to apply DFS, you have to look for R to B. After that, you have to compute the LV values. That is done bottom up. When you compute the LV values itself, you can report all the articulation points. Once you do bottom up, when you computed all the LV values of this, when you go back to this node, you can check whether this condition is true for all the nodes. If that is not true, then you declare that it's an articulation point and keep going up. Right, so that requires you to do another traversal of the DFS tree, not actually on the exact tree. But when you want to compute these LV values based on the back edges and the tree edges, that could be R to B plus C again, because you have to look at every edge and take the minimum value, right? So in other words, you are essentially applying DFS more or less like twice. So this complexity of this algorithm is R to B plus C. Then we have what is known as bridges. So bridges are essentially the vertices, edges whose removal actually disconnects the graph. Okay, so in this case, if you look at this edge and this edge, they are bridges, because if you delete this, this graph is disconnected from this graph, and this graph is again disconnected from this graph. So if you look at a tree, then every edge is going to be a bridge, right? Because tree does not contain any cycle, so it's a connected graph. The moment you delete any edge, it becomes two connected components. So every edge in a tree is a bridge. Okay, and if there is a leaf node here, that's going to be again, so the parent of the edge which is connecting to that is going to be a bridge. Once you delete this, then the rest of the graph is this. The same property is true for this edge, so this is going to be a bridge. So let's try to apply DFS again on this graph. Let me start with A, then I will go to B, then from B I can go to C, From C there is a back edge to A. From C I can go to D. From C I can go to E. Okay. So now I can compute, I can also note down what are the discovery times. Discovery time of this is 1, 2, 3, 4 and 5. After that you go back. Now you can compute what is also the L value of it. So the L value by definition of this is 5. Okay. For this is 4. For this it's, what is the L value for this? 1. Because there is a back edge which is going back to 1. What is the value of this? There is nothing which is going back to it, but there is a tree edge. When you look at the tree edge, you look at the L value of this, right? So that's 1, and this is also 1, right? So when you did this computation, when you go back, can you also identify what are the nodes which are going to be bridges? Again, let's say that the back edges are not going to be the bridges, right? It's only the edges which are part of the DFS tree are the candidates for your bridges. If there is a back edge, if you remove the back edge, the tree is still connected because you have the DFS tree of it, right? So if you look at all the back edges, all of them cannot be bridges because when you delete that edge, it's a back edge, right? Essentially means that you have the DFS tree. So there is a back edge which is going from here to here. If you delete this edge, you still have the DFS tree. That means the graph is still connected. It's only the edges, the tree edges that you have in the graph are the candidates for the bridges, and the ones which are not there in the tree edges are essentially called the back edges. They are not the candidates for the.
Can we say that the edges connecting the articulation point are the bridges?
Not necessarily, right?
No, sir.
Huh? See, if both the endpoints are articulation points, then the edge connecting them will be a bridge. Right? But that's only a necessary condition, right? Because when you delete both of them, the graph becomes disconnected. Right? So if you delete this edge, again the graph is going to be disconnected. But the other way around is not true.
Yes.
Has to be true.
If it's not a leaf,
See, if you look at the tree, and what I said is that every edge is a bridge. Okay, but in a tree, not every vertex.
sir, other than leaf nodes, sir, so leaf nodes will always be a bridge.
Yeah.
If not a leaf node, then these two nodes have to be articulate.
These two nodes, if it's not a leaf node, then both the endpoints has to be necessarily articulation points.
Yes, sir.
See what? So what I am saying is that if you remove this edge, okay, this graph actually becomes disconnected. But when you remove this particular vertex, you not only remove this, but also remove several edges. Okay, that means you are removing more edges when you say that this is an articulation point. When you say that this is a bridge, you are only removing one vertex, one edge.
So, but if that one edge can remove it, then removing the point will definitely disconnect the graph.
I mean, if a single edge exists between those 2 points.
If you removal of this edge actually disconnects the graph.
Then removal of that node will definitely disconnect.
Not true, right?
This edge is removed if you remove that node.
Yes, sir.
Sorry? If you remove this particular edge,
If you remove the one node first, it's as good as removing this edge also.
yeah,
So if this edge alone can disconnect the graph, that node will definitely.
yeah, that's correct, right? So that is true. If this is a bridge, then one of the endpoints,
Both.
both endpoints, it's the other way around, right?
So, but whichever node you remove, this edge will get removed.
Yes, sir.
So both of them have to be.
If removal of this edge, if this is a bridge, okay, let's say that this is a bridge, that means that if you remove this, the graph actually becomes disconnected. Okay, that means when you want to come back to this vertex, when you remove this vertex, you are not only removing every edge which is adjacent to this. Okay, that means that you are also removing this edge. Okay, in that case, the graph becomes disconnected, right? The same thing is true for the other one, right? So if both of them are not leaf nodes and internal nodes, then if you look at any edge, if it's a leaf node, then what happens?
Directly.
So, but there can be back edges, right? In the DFS tree,
Oh, if it doesn't have any packages, then
yeah. So if you look at this back edge, you look at the if it has a back edge, then it's not a then this is not a bridge. Okay. Otherwise, if there is no back edge from here, then this is a bridge. Now, if you look at any intermediate node, both of them should be articulation points in order to make this graph to be bridge to be the same. Okay, so yeah, so you can apply the previous algorithm and do this. Yeah. Yeah, there are no bridges here. This is not a contradiction. If it's a leaf node, then obviously this thing is yeah.
So in that one, we
In this case, both the edges both are.
in that example, if we consider D as the source, I mean the example of that bridge page. I mean slide of.
Okay. Which is the one you should consider as a. Yeah?
I mean we can consider D as a source.
See, this is a bridge because this is a leaf vertex.
Yes, sir.
The
But,
moment you start, this is a leaf vertex, then this is going to be a bridge. So now,
I mean,
so this
see
is also
now-
an articulation point. This is
But-
also an articulation point because when you
Okay.
delete this, this graph is disconnected. When you delete this, this again going to be disconnected. So both the endpoints are articulation points. So here B and C are articulation points. So this edge becomes an articulation point, but the remaining three are all leaf edges, leaf nodes connected to the leaf node. They are anyway this thing, and moreover this is a tree. In a tree, every edge is a articulation bridge. Okay. So you essentially do the articulation point algorithm again, but you can have a simpler algorithm in this case because when you look at this particular edge, I know that this will be a bridge if there is nothing which is connecting from this to the above one, right? So that means that you look at u comma v. So the LU of v is smaller than or equal to discovery time of v. Okay, then this is a bridge, right? So this is a bridge. That means that you might at most connect to this level. Sorry, if there is something here which is going back to this level, it's still fine, right? Because if you just delete this edge, this is still connected. But if this is
Yes, sir. Condition is
less than or equal to this, then this is not a bridge. Okay, if L value of this is smaller than or equal to this, then this is not a bridge. And otherwise, this is going to be a bridge. That's it, right? When you do the calculation, when you go back, you can check every edge in the tree, and then for the leaf node, so the leaf node, just immediate above vertex of edge will be, see, because what happens to the leaf node when I look at this, this will be the discovery time of this, and the L value of this, so the L value of this is something else, the discovery time of V is something else. This is certainly greater than this value, right? So L value is greater than this. In that case, this condition will take care of this case also, because the L value of this will be the discovery time of this. Discovery time of this is greater than the discovery time of this, right? So, so that will take care of the leaf nodes as well. Say graph is biconnected if there are no vertices whose removal will disconnect the graph. In other words, a graph is biconnected if there are no articulation points. In other words, if you take any two vertices in the graph, there are essentially two different paths there, right? So that if you remove one vertex in the graph, there is still connected in the other direction. Okay, so this is a bi-connected graph because it doesn't have an articulation point, and this is not bi-connected because if you remove this particular edge, then whose removal disconnects the graph, right? So now the question is, I want to know whether a graph is bi-connected or not. For that, algorithm is easy. You just apply the algorithm for finding the articulation points. If there are articulation points, then
It is not
then it is not a bi-connected graph. If there are no articulation points, then the graph is connected. So if the graph is bi-connected, okay, so then what I want to actually do is to find what is known as the bi-connected components, right? So what is the bi-connected components? I want to divide the set of vertices into subsets, exactly same as the way I defined strongly connected components, right? So strongly connected components are a set of vertices, so that if you take two vertices within the same connected component, there is a path in both directions, but that property is a maximal in the sense that if you take two different vertices in two different connected components, there is no path in both directions, right? That's the definition of the strongly connected component. So what is the bi-connected component now? If you look at any connected bi-connected component, that should not have an articulation point. In other words, that component is bi-connected. But so it's a component in the sense that is a maximal with respect to that property. In other words, if we add one more vertex to this, then that property is no longer true, right? So in this case, if it's a bi-connected component, there is only one here. So now you can divide this into two parts. One is this part of the tree, another one is this part. Okay. Now if you just look at ABC, that's a bi-connected component, and you look at D and E, that's another bi-connected component, right? So you essentially look at the bridges, and this not even bridges, right? So this part becomes this thing, right? So essentially there was a articulation point which you put it in one side so that the other one becomes this. So the bi-connected component problem is to find the bi-connected components of a graph, right? So a undirected graph. So if the graph is already bi-connected, then you essentially get only one component. Otherwise, you will essentially get few components. Just give some different numbering to these components. Let's try to apply the DFS on this graph and see how to compute the bi-connected components. Okay. Let me start with the vertex 1. Okay, so I discovered 1 first, then I went to 2, then I went to 3, then let's say I went to 4, then I went to 5, then I went to 6, then I went to 7, then I went to 9, then I went to 8, okay, then I went to in that case everything is connected in this case, right? So you this graph is going to be bi-connected in that case. Okay, so from here I can go here. Once I go here, I can come here, come here, come here, right? So yeah. So but this graph has bi-connected components. So sorry, yeah, let's just complete this. I'll come here 11, let's say 12, 13 and 14. Where did I miss the numbering?
On 9 you
Sir, 5. I mean that.
Yeah, so there is no 8 written, right? So I should have written 8 here, 9 here, this is 10. So you can make this as 11, this is 12, and so this will be, so I am going back, right, in that case. So this will be 15. So I am writing the discovery times.
So 14 only.
Sir,
12
14
and
only.
15.
So 11, 12,
No, sir, I mean 10, 11, 12 and 15.
so 10, 11.
No, the 11 would be 11.
Yeah, so you can do either way around, right? You can do either way around, right? So because I can come from here, I can go here. When I go here, I can come here. After that I have to go back. Okay, so the 13 is gone.
14, 14. Okay.
This is 11, this is 12.
11 and 14.
When I come back here, it's 13. So this should be 14. Clearly, this is not. From 1 you can reach all the vertices, but that doesn't imply that there is only one connected component, right? So certainly, clearly, I see. Are there articulation points in this graph? For example, what is the articulation point here? 12, 10 is also a articulation point, right? So if you remove this vertex, this graph is disconnected. And on this side, do you have a this thing? Okay.
Everything is
Yeah. So now let us write down the L values. Okay. So from here you can't go back to anything, right? So this is 14 itself. From here you can go back to 10, right? So I'll write it as 10. From here you can still go back to 10. From here you can go back to 1, right? Since you can go back to 1 from here, from this vertex you can go back to 1. So from everywhere you can go back to 1. Okay, so when you do this computation, you already know that this is the slowest vertex. So when you look at LV value is smaller than or equal to dV value, all this turns out to be non-articulation points. So now, how do you divide the graph into parts such that you only get connected components? You have to divide with respect to the articulation points. So what is the first articulation point that you see? 12 is an articulation point. So you can make this as one connected component. Okay. So now you go back to 11. Okay. And when I come here, yeah, this is still an articulation point. So you can make this as one connected component. And the rest of the graph is, there are no articulation points there. So you can essentially, that becomes one connected component. Right. In general, what is my algorithm now? So for to find the biconnected components, first I apply DFS, find the discovery times, and then come back and find the LV values. When you do the back computation, you know what are the points which are going to be articulation points. So the algorithm says that when you traverse the edges, the edges in the order of the DFS tree, keep pushing them into the stack, right? So when I come here, you have essentially pushed all these vertices into the stack. When I come here, I pushed everything into the stack. So now when I go back, the moment I hit a articulation point, just pop out all the edges till you get the edge, this edge. Okay. So now you pop this edge out, so this becomes one biconnected component. Now you go back here, you push this one out. When you reach a biconnected component, you push pop out all the. In other words, when you traverse the edge, you keep pushing the edges in the both the tree edge and the tree edge and the back edge into the stack. And when you start backtracking on the DFS, the moment you get a edge. Okay, so the moment you hit a edge such that this is V and this is U, such that the LV value, so you expect LU value to be strictly smaller than DV value, right? So if this is true, then it's not a articulation point. But if this condition is not true, the moment you hit such an edge, you start popping out the edges from the stack till you pop this guy also out, right? So whatever vertices that you get, give them the same numbering, they are in one biconnected component, right? Let me repeat, you apply DFS, then compute LV values, LU values, then start applying DFS again on the actual graph. Whenever you look at a tree edge or a back edge, keep pushing them into the stack. When you do the backtracking,
right? So when you computed the DFS, when you reach here, you start going back, right? That's essentially what is backtracking. When you look at an edge pi of u comma v in the tree, if this condition is not met, okay, if this condition is met, you just don't do anything, right? In that case, you keep moving. So this is why you backtracking. If this condition is not true, you start popping out every edge from the graph until you pop this particular edge from the stack. Okay, and whatever you get will be in one connected component. Just repeat this. Okay. So why is that true? Because when you do start doing backtracking, the first time when you hit a articulation points, everything below that in the tree you are making as one biconnected component. So that certainly is a biconnected component because that does not contain any articulation points. Because if this part of the tree had an articulation point, then you would have start popping out earlier. Now you do the recursion again. Right, so if whatever was traversed earlier, right, so I am looking at a tree of this kind, so this has different parts. So you pushed everything here, there was no articulation point, so this became, so this is a different one. And what happened is that when I came here, this happened to be the articulation point. So all these edges are still there in the stack. This is, since this is an articulation point, when I do the backtracking and reach here, whatever vertices are there, I just collect all of them and make as one connected component, and then remove this, and these edges are already there. Then you start traversing the rest of the graph, right? So when you do the backtracking, see if this condition is not true. If the condition is not true, start popping out everything till you pop this edge out. That means that you are essentially looking at all the edges in that subtree. Right, so when you're popping out all the edges, essentially means that whatever you popped out inside that, right? So this is what you do when you do the backtracking, right? So that means whatever elements were there, which were not part of the other connected component, because if there was another articulation point inside, I would have popped those edges earlier, right? So whatever is left, all that you collect and make as one biconnected component and just repeat this, right? So this is again traversing the DFS tree again once more. But you need a stack of size order V in order to implement this. If this is a biconnected component, then this condition will never be true. In that case, you will push all the elements into the stack, and finally you pop everything out. So that essentially means that there is only one connected component. So you can find the biconnected components in a undirected graph in order V. Okay, let's look at some more problems, probably in the context of the shortest paths. You are given a graph. This you can look at as graph of different locations in the city, and you are also you essentially know the distance of these edges. Okay, these could be bidirectional edges, or it could be one directional, right? So if it's a directed edge, means that is written like this. In other words, this is a one-way traffic. If there is no edge mentioned by that, you can travel in both directions. So there are some locations where there are, let's say, hospitals. Okay. I want to compute for every vertex what is the distance to the nearest hospital. Okay, how do you compute that? So DFE for every vertex, I need to know what is the distance to the nearest hospital. I don't know which is the nearest hospital of this particular location. First you should find what is the nearest one, and then look at this. How do you start this now?
You can find all the biconnected components.
Biconnected components. This is a directed graph, right? This is a mixture of both directed and undirected, so you can't talk about. Yeah.
So we can go to every hospital, use shortest path for all the points in the graph, whichever distance is minimum.
Yeah, so you can. So if there are k shortest paths, the hospitals, what he is saying is that from every hospital you apply delta, you get the distance from that hospital to the vertex V. So you compute d1, d2, dk, and keep track of the minimum. Right, so when you compute these distances, you can have d of e as one element, but you update this d of e only if it is required. right? So if the distance that you are looking at is bigger than DFE, don't update this. That's fine, but the only problem with that is that so you have to run the algorithm k times k into order v plus e log v, right? So, right, and k can be v by 2 or it need not be constant. So can I do something faster than this? In other words, I am looking for an algorithm where you apply DSA's algorithm only once, right? That means I am looking for a complexity which is order v plus e log v. So I don't want to apply DSA from every hospital. So the what I am looking at is the other way around, right? So I want to find the shortest path to every node. I want to find what is the distance to the nearest hospital. Does this have anything to do with the minimum spanning tree? Let's say that this is. Let's assume that this is a direct undirected graph.
So then you can do BFS, and then backtrack and try to find the shortest.
So
The BFS only works when the it gives you the shortest length path only when the all the weights are 1, right? So the distance between two cities could be different.
so we
Then you can
can
build a minimum span.
No, the weights are not 1, right? The distance between two cities, the weights are not 1, unit weights. So now you want to build a BFS
Minimum.
minimum spanning tree. Can you get minimum spanning tree and then?
And then from the leaf node you start calculating the distance between the hospital, and then at every parent node you add its weight.
This works. So what he's saying is that find the minimum spanning tree. Then from the leaf node you start going up. So wherever, so you are essentially here, you are essentially here, you are essentially here, and so on. So what he is essentially saying is that from this node, if you start here, if this happens to be an hospital, the distance from here to here is the nearest one. In other words, if this is not an hospital, then you just go to the ancestor. The first one in there will be the nearest hospital.
And you can do from top.
You can top bottom also you can do. That's what he says. So what you can do is that you start with the root and keep going down. So if this is a hospital and the child is also an hospital, you just forget about this and start here. From here, when you come here, you just keep adding the weights. When you reach happens to reach a leaf node, when you do the backtracking, you finalize the numbers, right? But if you hit a hospital again, then you initialize the this thing to 0. Yeah, 0, and then just continue this. Is this the correct algorithm? Huh? May not work? Quick example where this doesn't work.
So if you have a cycle and
Yeah.
one of the edges is very.
So essentially, this is an edge. This is sorry, my cycle is a problem. Okay. So you start here. This all the edge weights you can consider as 1. Okay. All the edge weights are 1. And so this is the vertex where you are starting there, and this is your hospital, okay, and the weights on all these edges is 1, okay, all of them are non-hospitals, okay. Let's say that there are 1 billion such nodes, okay, and this is just 2, right? Since there are 1, 1, 1, 1, 1 here, your minimum spanning tree is essentially, so since the weight of every edge is 1, so you remove this edge, that becomes the minimum spanning tree. Since none of them are hospitals, this is the only guy who is a hospital, which is at the root node. So you will end up reporting that the minimum distance to from here to the this thing is 1 million, right? So 10 to the power 9, but actual distance is only 2, which is an edge which is not part of the minimum spanning tree. In other words, this is also an example to show that the shortest path need not be part of the minimum spanning tree, right? So minimum spanning tree essentially tries to connect every vertex in the graph, right? So but the shortest path is only between a relationship between two edges. Yeah, so this fails, then what do you do now?
So from every hospital you can check its immediate neighbors and update its values.
Yeah.
And delete, add them to the one that you already know, and then update its neighbors values.
So which is the order which I took one vertex, I look at all the hospitals, I look at the neighborhood of that and update the distance to all of them. Okay, that's done. After that, how do you, once you do that, then there are still some locations which are not reachable, right? So now what is the vertex that you should start with and then try to connect
So
it?
the minimum distance.
The distance, the minimum distance from where?
From the ones which have already been added.
Yeah, probably, yeah, correct. You're more or less there. Let me give you an alternative algorithm. So let's look at, these are the vertices. Okay, let's look at the locations where there are hospitals. Okay, let me add one source vertex which is called the source and connect this node to all the hospitals. The weight on these edges is 0. Okay, now we apply Dijkstra from this vertex S and compute the shortest distance to every other vertex. Okay, so what I did, I added a source vertex, I essentially connected everything to a hospital. Okay, weight of this edge is 0. Now you apply Dijkstra from the source. When you apply Dijkstra from source, you essentially are trying to find the shortest distance to a vertex V, right? So the distance to V, my claim is that this is the distance to the nearest hospital. Why is that true? When you find D of E, which is the distance from the source to that particular vertex, that will be the length of the shortest vertex. That will be the distance to the shortest hospital. Why is that true?
So because we only have one path from S to hospital and then we
So in the path from S to hospital, S to the vertex V, the immediate one will be an hospital. Right, so in other words, in the backward direction, before you hit the source vertex, you should kindly get an hospital. But can there be another hospital here? So in this path from here to here, can there be another hospital here? Why is that not possible? So in that case, this vertex would have been connected to this here. So in that case, this weight of this path is positive. Instead of that coming here, I could have come here and gone there. That would have been the shortest path. So that means there are no other hospitals on this path from the source to the vertex, right? So you can backtrack, and weight of this path is the so the length of the shortest path from this vertex to this hospital, and from here to this is anyway 0, right? So you don't have to add anything there. And if there is a path from this thing to another hospital here, just connect to this. The length of this path should have been greater than the length of this path. If this is shorter than this, then the Dijkstra should have reported that. But when you try to implement this using Dijkstra, what it will do is that it will add S with the priority 0. Then it will locate all the edges outgoing from here and add all these vertices where there are hospitals, and priority of all of them is going to be 0, right? After that, your Dijkstra will take care of it, right? Instead of so this S that I added is only an implicit representation. When you implement this, you don't have to implicitly add S and then connect to everything. What you can do is that you look at all the hospitals, all the locations where there are hospitals, you add that into the your heap in the beginning. Instead of adding the vertex S, you add all the hospitals with priority 0. Okay? So the what the Dijkstra did is that you started with the vertex S and then applied all the algorithm. Right? In this case, what I am saying is that you add all the locations where there are hospitals with the priority 0. After that, you instead of adding one vertex, you are essentially adding k vertices where there are hospitals with priority 0, because from that location, reaching that location is 0. Right? So after that, you essentially apply Dijkstra from that location. Right? So that complexity is essentially you are applying Dijkstra once, which is order V plus E. Okay, let's look at the next problem. So you are given a graph, and instead of the edges in the graph, the vertices are weighted here. Right? So there are weights which are written on the this is 2, this is 4, this is 5, this is 6, and this is 8, and so on. So there may not be this is the directed graph. So from the vertex V, I want to know what is the maximum weighted vertex that I can reach from this vertex. You can think of this weights are as populations, right? So the bigger the weight implies that this is a bigger city. Okay, so what I am asking is that what is the largest city that I can reach from the current location, right? So is the essentially if U is reachable, so the D of V is defined as the max value of every vertex is right. So the weight of the vertex V, weight of the vertex U, such that U is reachable from V. For every vertex, you ask the question, what are all the nodes which are reachable from this, and keep track of the maximum, right? So the D of V, if you want to compute by brute force, you start with V, you just apply BFS at DFS, whatever vertices are reachable, you keep track of the maximum weight, and assign D of V to be the maximum of that, right? So if you want to repeat this for every vertex, then it's order V plus E into V, because you have to repeat this for every V. So that is order V into E. So can I do something faster than this?
So you find the number of connected components.
The number of connected components?
And then the maximum value for each connected component will be all the dV.
Strongly, this is the directed graph, right? So if it is a directed graph, so the directed graph, the strongly connected component says that you have to have the edges in both directions, right? So what may happen is that you might have strongly connected components like this. So there may be edges from here to here, but not in backward direction. There may be edges from here to here, there may be edges from here to here, and this connected component has the maximum weight. In that case, everything happens to be the maximum, right? It does not mean that the maximum valued weight should be there in the same connected component, strongly connected component.
So we can look for bi-connected graph, and
You can talk about bi-connected component only if it's a undirected graph.
Okay.
So this can be directed graph, or it can be a mixture of directed and undirected graphs. So alternatively, you can start with the vertex which has the maximum weight, and then apply DFS from that DFS or BFS from that vertex, right? So you look at the maximum weighted vertex, then you apply DFS or BFS from that. So whatever vertices are reachable from the graph, can I do that?
Sir, the unreachable. Yes, sir.
Yeah, how do you take care of that?
So
I want a path from U to V, but so if I apply DFS from that, then there may be a path in the opposite direction. So what is the graph?
Smallest number.
So what is the
Start with the smallest number. Smallest weight.
smallest weight will not work, right?
no, sir.
So I want a path in the opposite direction. How do you take care of that? Yeah. So a strongly connected component, this is the problem, right? See, if I start with the maximum vertex, you have to find the DFS of it, and there is a path from here to here, but I wanted a path in the opposite direction, right? Then all these vertices will have the this maximum as the value, right? So how do you quickly fix this problem?
Sir, take a transpose.
Yeah, so just don't work with the actual graph, work with the transpose of the graph, right? So what you do is that you take the graph G, take the transpose of the graph. What is the transpose of the graph? The adjacent in the opposite direction. Okay. How do you find that adjacency list? You go through the adjacency list and reverse all the edges. So you have E transpose now. Now you take the maximum vertex and then apply DFS on that from the transpose of the graph. Whatever vertices that you collect, D of E has to be that value. And then among all the vertices which are not visited, pick the vertex with the maximum weight and then repeat this. What is the complexity of this? Yeah?
E plus B.
Why log B is coming into picture? Yeah, so you have to first sort them in the decreasing order of their weights on the vertices. That will take V log B. Then you are essentially applying DFS. Once you apply a DFS on that, then you traverse through the list. The next vertex which is unvisited, that is known by the color of that particular vertex. You start applying DFS from that vertex and then just apply. Right. So this will be order V log V plus E algorithm. Right. So V plus E is the complexity for applying DFS. I think it's a good time to stop here. That's more or less end of the course. The Friday there will be no class, but you have to submit your assignments by tonight. So next week will be the exams. I think you remember that weightage for the end term exam for theory is 30%, and weightage for the lab is about 25%. On Friday, I'll send you the list when you had to appear for your lab exam. Right? So either on Monday, Tuesday, so that's it. And if some of you have problems with your marks that is assigned so far, please meet me on Friday at 2 o'clock. We will get it resolved. Right? So whether the midterm or any other test, if you still have some questions, we can get it resolved by this Friday. And probably I'll give you the marks for the end term by next Thursday. So if you want to look at your answer sheets or something like that, you should meet me on Thursday evening. Okay, next week. Okay, so that's only for the end term. But before the end term, whatever problems are there, we should get it sorted by this Friday, 2 o'clock, 2 to 5. Okay, I'll stop here. Thanks. So the end term syllabus is everything that is done after the midterm. but you can expect more questions from the graph algorithms. So again, so there will be questions for 40 marks. You had to answer only for 30. So do you want an easy exam or a tougher exam? Easy exam? Why? Large course. The grading is relative, but you need 80% to get an A. Yeah? Easy. So you need 80% to get an A and 60% for B, 40% for a C. So in between that is relative. But these numbers are hard numbers. Okay, so the exam will be tougher than whatever exam that you have written so far in the course. Okay, mentally be prepared accordingly.
You're not coming.
ట్రై చేస్తున్నారు 80% అండి ఎవరికి వస్తుంది
నీకు వస్తుందిరా
రికార్డ్ అవ్వలేదు